is putting the synthesis into the silicon through a cable. I will show you the cable. So it's downloading through this cable here into the chip there the circuit. So now I have a two-level of programmability. With all this process, I can program the circuit. The FPGA means putting my own circuit. But then I have a program memory inside that still allows me the flexibility to change the algorithm. Next step, the chip will cost much less. I don't know what to say how much, but close to the order of magnitude. And I will lose one programmability, that is the one of the circuit, but the circuit now is finally defined. And it's a circuit that has an instruction, so it allows me still to change the program. And I will keep the flexibility of changing the program, the programmability. Now we come to the concept, the simulation, and now the hardware, and on the scope, what is it doing? The goal is we get a set of data from the detector. It goes to a set of data from the detector. It goes to the first layer of processor. This processor starts the execution, but before it finishes, there is another data coming. So without having a multiplexer, but with this way of organizing the chip in a sequence, and there is a switch that it gives the advantage of having equal distance, I send the data to the second layer, and then I send it to the third layer, but not directly to the third layer. It goes from the top, from the detector to the first layer. Next clock, it goes from this to this, then from this to this, and so on. So then I mixed input data, output result. So in the middle of the chain, you have a flow of output data, input data, output result that go to the pipe. At the end, you have only output result. Okay. So what is the oscilloscope showing? The oscilloscope is showing that we get a data here. This is the activity of processor, this one here. There are 4 processors inside. I just take one. So low, it means that it's running. High, it means that it's on hold. And it's a data-driven processor. So from here to here, this is the execution time. The program that is executing is this one. Each line can be 26 operations. There on the back, now let me turn this. You have the 26 operations that here are described in binary. However, I have an assembler and I can describe in mnemonic. Okay? So these are the operation that I am executing during this time. However, before I complete the program, there is another data coming. So that is passed to this other chip here, is executing there. The reason why I have 2 spikes here is because this is branching twice, and this is branching one time, means this has found the cluster, and the other one did not find the cluster. Now that we have seen the timing, means that is the flow of the data is correct, let's see if it does the good operation also. And the good operation is, we would like to find the 3 by 3. Okay? So I have put here 4 switches and 4 switches. These 4 switches is simulating a photomultiplier at time number 0. These other 4 switches simulating the same photomultiplier at time number 1. So I would like to change the data because the data has to flow. I should not have the same data flowing. So I put a set of data, and then at time 1 I would like to change the data. And so I would like to see the result. These are the 4 switches. I made a wire connection between this and this. I made a wire connection between this and this, and the same. So at the end, even if physically I have only 4 processors, because of the wire, I have a 6 here, I will have a 6 there. I have a 4 here, I have a 4 there. Okay. So what I do, this is the set, okay, in binary. You look at the switch, this is this and this are up, okay? So this and this up. Let's look at this, okay? This is 20, 4, 2, and this is 6, okay? So the result is, add up all this, 48. Look at the result. The result is, what is the LED? The third and the fourth. So it is this LED and this LED. It's 32 plus 16. Okay? Now, this one, I put a different set where the highest is this one, that is 38. Okay? So I can change it. And now the cluster is not the cluster, this is the cluster. Because it becomes higher. Now if I put it on this one, then that is the cluster. Okay. And it's giving me, so it's finding the cluster, means I am the greatest than everybody, and it's giving me the total sum. And it's doing this, Jerry, you can have this is 200 nanoseconds time scale, so you get the time scale are 2 square. We have to consider also that 1, 2, 3, 600 nanoseconds. Okay. So by calculating the decay time of the crystal, the complexity of my algorithm, I determine the number of stages. And I will have an electronic debt-free, programmable, that can execute all the algorithm to find the oblique photons, to find the good energy resolution, and all that. So that is from concept to application. Now, what do I get from this? The first information that I get from this is what Baroni asked me. And here we go. We got, the reason why I'm using 2 power supply is because 1 power supply is powering these test boards, because I won't like to separate, I like to measure the other one. The other power supply is only supplying these 2 boards. Now, these are the voltage. On this chip, I have 2 voltage. The 3.3 volt for the I/O, 1.8 volt internal, the core. Those, you see, 1.8 volt is on the left, 3.3 volt is on the right. Now, if I move this meter, and I get the consumption, 600 milliamp, and another 600 milliamp, 620. 2 chips. So divided by 2, that it gives me the power consumption per chip. That is 1 watt, a little more than 1 watt, 1.2 watt. Okay? So again, this is a full FPGA consuming much more silicon area for time. But I have 2 important parameters. So I move to the other room, and we just move to the other room and see what I do with these other 2 parameters. If they will allow me to build the board, because I couldn't start the board unless I have these 2 parameters.
Let the cameraman go first.
Thank you. Okay. So now I can determine the power dissipation on this